I think, it's pretty well documented that, from bench top to deployment is at a minimum 10 years, if not, and this is across sectors,
Yeah.
right? So with respect to that, you know, I think there are a lot of innovative approaches with respect to nuclear fuel recycling that are still underway. I think that if we made some serious investment in those, we would be able to get those de-risked to the point that you could talk about scaling. So that would be kind of my first one. We're seeing a lot of promise there, but I think that this sector does need more investment to do it the way that I've been talking about.
Just because the facts are A, if the narrative is B and everyone believes the narrative, then B is what matters. But it's our job in our industry to speak up proudly, soberly, and to engage people in this dialogue. Those 2.5 billion people that are in energy poverty, they need us.
America cannot meet this threat alone.
If there is a single country,
of course, the world cannot meet it without America.
that is willing to
We're going to need you, the next generation, to finish the
overhaul
job.
nuclear regulation
We need scientists to design new
and
fuels.
focus on net public
We need
benefit
engineers to invent new technologies. We
over absurd levels of radiation
need
protection,
entrepreneurs to sell those
then
technologies.
we will march towards this.
We need workers to operate assembly lines that hum with high-tech, zero
where we
carbon
have
components.
unlimited prosperity for all humans.
We need diplomats and businessmen and women and Peace Corps volunteers to help developing nations skip past the dirty phase of development and transition to sustainable sources of energy. In other words, we need you.
Hey, welcome to another episode of the Fire to Fission podcast, where we talk about energy-dense fuels and how they can better human lives. My name's Mark Hinaman, and today I'm joined by Dr. Jenifer Shafer. We clarified ahead of time. I can call you Jen. We can talk informally about this. But really excited to chat with you today, Jen. So Dr. Shafer is a professor at the Colorado School of Mines. She also has experience in government, specifically ARPA-E program stuff. But today, I think we're going to focus on kind of your background and a bunch of the research that you've done in your career and research program, and we can save some of the other stuff for a later episode. So we've already agreed. Maybe a part 2 could be really helpful to have. So
Yeah, sounds great. Thanks for having me, Mark.
yeah, absolutely. So Jen, let's jump right into it. Where'd you get your start? Like, give us perspective on where you're from and what got you interested in energy, and yeah.
Oh, yeah, sure. Well, so I got my start. Well, and you could start very far back, but I'll start with my first inoculation in nuclear, which was in a high school science course. And we had a 1-week nuclear unit where just the teacher took it upon herself. She thought it would be appropriate to expose us to this, all the puns intended. And I thought that that was fascinating in and of that. And I continued on with my scientific career. And I think one thing that can be really helpful a lot of times when I'm talking, I'm noticing that, fortunately, we're getting younger and younger people in this field that while now we're seeing solar and wind and things of that nature contributing significantly to our energy production on a given year, at the time when I was going to undergraduate, these were just a blip on the radar. These were just a blip of maybe they could be a thing. And nuclear seemed like the only option if you were serious about, continuing to power our world and continuing to, or also providing low emission electricity, right? And so this was fascinating to me. And the more, perhaps naively, perhaps whatever, while I was sitting in Colorado, a state with no operating nuclear reactors at the time, it seemed, why didn't we have more nuclear? And it just seemed to me like the waste. It was, if we didn't have the waste challenge, that it would be easier for people to buy into nuclear, and this would be something that could be really catalyzing to work through. And, now that I've been in the field longer, of course, I know that it's not as simple as just the waste. There's a lot of compounding factors that impact that. But it was something that was on the back of my mind. And as I continued with my degree in chemistry, and learning more about what I call the foundation, not the basement of the periodic table, elements like uranium and plutonium that had really dictated the course of human history for what felt like, a time block of almost 60 years, right, between the Cold War and other things. It seemed like these were both really important facets and also things that weren't particularly well understood. And so, those combining and convening interests led me to complete my graduate work at Washington State University, focusing on nuclear fuel recycling and the technologies that could be enabling there. Spent a little bit of time at PNNL as a staff scientist, and then I've been at Mines now for about a dozen years. So with a research group focusing not only on nuclear fuel recycling, but also national security as far as technical nuclear forensics and nonproliferation, and trying to understand all of the intersecting facets that could be helpful in deploying nuclear energy.
That's awesome. What an intro. I feel like you just covered the whole gamut of like, well, these are all the broad level things that I've done. So let's dig in. Starting with, okay, so undergrad was CSU, right? Colorado State.
Undergrad was CSU. Yep.
Yeah. Okay. I got to say, go Buffs, right? Just
it wouldn't be a discourse if there wasn't a little jab here. And
for non-Colorado natives, that's, the Colorado Buffaloes versus the CSU Rams. There's a ever rivalry. Even though it's not really real, it's just kind of fun to say.
Well, while I was going to CSU, it was in the Bradley Van Pelt days, and we were doing quite well. So, not as well as this. I mean, now CU has definitely been at the helm of this, but at least for a blip in the radar, we were quite competitive there.
You guys almost beat us last year. I was at that game. It was not necessary to rush the field. But, so wait, I mean, wind and solar weren't really discussed, and I mean, you're not that old, right? Like you said during your undergrad. Like when was that? That's interesting,
right? So this would have been undergrad, would have been 2002 to 2005, right? So this is the sort of thing where, especially if you look at deployment, right, you didn't see it. They were definitely being discussed, but it was in that point where you were kind of looking around going like, I don't see how this is going to work out really, and you're just starting to see these things happen. So,
and then by the 2010s, people were believing, right?
People were believing.
Yeah.
Right.
It came in like at the onset of that boom. And I wasn't a believer either, but if I could have predicted the future, I would have made a different bet. I did make a different bet. So.
Well, right. And that what they say, usually if I had that much control over time and space and the ability to predict, I'd be in a different job than I am now. So.
Yeah, exactly. So what about chemistry was interesting?
Oh. So chemistry, it's funny, at CSU, I started off as a sociology major with a minor in criminal justice. And
That's
that lasted
chemistry. Yeah.
that lasted for precisely 1 month. My favorite movie at the time would have been Silence of the Lambs with Clarice Starling as a role model there, and I was thinking I was going to be some form of a psychological profiler and things of this nature, and I existed as a sociology major for 1 month until I decided that I wasn't really enjoying the coursework. But at the time, also, of course, Crime Scene Investigation, you might remember, was a pretty major show on television. And so I had at least positioned myself such that I was taking the chemistry for scientists and engineers at CSU. So I was able to transfer from a sociology major to a chemistry major without any impact to my degree timelines whatsoever. And then as I continued to take chemistry courses, I got good advice to start doing undergraduate research, which I loved. And then over the course of that undergraduate research, one of the opportunities that presented was the Nuclear Chemistry Summer School, or as I say, boot camp for nerds. So this is a program that the Department of Energy has run for about 35 years now. And it was born out of the recognition that we had a fractured pipeline as far as recruiting nuclear scientists. And so they actually intentionally try to recover students who are at institutions that don't have really a nuclear background within them. And so I was able to go there, get more exposed to the field. And that it's a 6-week boot camp. It's 3 hours of lecture in the morning, 3 hours of lecture in the afternoon. You get 6 credits. It lasts for 6 weeks, and you also get a stipend. And I thought to myself, well, at this stage in the game, they're willing to cover my tuition. They're willing to pay me professionally as a student. It seems like the job prospects for nuclear actually increasingly looking more and more interesting. And so those are some pieces there and how the chemistry came along.
Wow. Just nerding out. I love it.
Just nerding out. And it was also there where I was introduced to the concept that our nuclear waste is, 95% of the energy value remains actually in nuclear fuel. And considering I already had the predilection that the waste was such a non-starter frequently for people, and I learned that we were only using 5% of it, I was, with a chemist and wanting to recycle, I said, hold the phone. This is where I have to spend some more time. So
Yeah. Can we touch on that or go off on a tangent on this idea?
Sure.
Because I should know this, and I'm embarrassed that like I think I have this misconception. People say that like the 95% of the energy is still there, but then for
Right.
low enriched uranium, right, we enrich it for U-235, right? For those watching
For
this
that
on
one.
YouTube, you got this fancy cheat, good old Generation Atomic. I heart U-235. Well, then it's like 5% U-235 at that.
Right.
And as I understand it, am I wrong in my conception that like spent nuclear fuel has the majority of that U-235 fissioned? Or is it like there's still, and that's why there's 95% left at the end of the life? I mean, can
Right.
you like
So it's a
walk through this
couple of
idea?
different things in there, and it depends on how you want to slice it and dice it and talk about it, right? So generally, when you have low enriched uranium in a reactor, right, you will burn it.
5% is U-235.
Yeah. 5% or less uranium-235. You will burn it down to a substantial fraction of much lower enriched uranium-235, or even below natural uranium content uranium-235, that 0.7%, right? So that is happening, but also at the same time, there is an ingrowth of plutonium-239, right? And so that ultimately ends up constituting maybe about 1% of the material that you have in there. And it ultimately depends on how you decide to run your fuel cycle with respect to how you're going to try and recover that material, right? So uranium-238 can be fission more frequently in fast reactors, though it does happen to a very limited extent in light water reactors. More often than not, what you're actually seeing is the ingrowth of the plutonium-239. So basically, through some combination of either fissioning the uranium-238 that could be fission or converted to plutonium-239, or by potentially re-enriching, which there is some precedent for this happening as far as bringing that uranium-235 content up. The reality is any actinide has the ability to fission and release energy, and it's on some level some conversation about what is the reactor that is going to be most enabling to go ahead and do that and execute that.
Got it. So I'll say it back. You start with 95% U-238, 5%
Right.
U-235.
Yes.
After you got fuel in a light water reactor for 18 months to 6 years, or you've got these cycles, whatever fuel cycle
Right.
goes through, then that 5% of the U-235 has presumably fissioned and then
Gets depleted.
other stuff, right? Burned up, even though it's not really burning. The industry uses the term burn.
We use the term burn,
It's easy for humans to conceptualize that, right? But and then 1% is plutonium-ish, but then that 95% number is kind of the rest of the U-238. It is fissionable, but through a different mechanism than in traditional light water reactors.
Yeah, you said that very well.
Okay, cool. I feel like that's a test for me, right? If I can say it back.
Right. If you can, recover that. And so if you're able to put the uranium-238 back into the reactor, it has the opportunity to, it's kind of a conduit for getting uranium-235 in a reactor, right? But it also is a conduit for potentially making more plutonium-239 that could be then fissioned and recover energy from as well.
Okay. You made a comment about this, and I love this idea. I've actually never thought about it before, but I want you to expand on it, or expound on it. The basement of the periodic table, right? Like when we think about the elements that exist in the universe, we have where did these things come from, right? We've got this theory that the Big Bang happened, and there's all these elements that exist in the universe, and like there's this heaviest of the natural elements, uranium, that just kind of exists, and it's really neat and can do super cool things. But talk to us a little bit about like what that means for these molecules, and questions that I've got are like, where did these come from? Did all the elements start as like these heavy elements? Probably not, but like, what does it mean? How much decay has there been?
Yes.
This might be kind of an abstract question, but it's
No,
fun.
in fact, so I am not a nuclear physicist, but I'll play one on TV or on a podcast for a moment, deferring to
Hello.
the reality that there are people that can speak
Have
with
all
this
these
with
gate chains memorized and can spout
yeah,
them.
much more fidelity and nuance than I will, right? But I mean the basic rub of this, right? So you do have the Big Bang, or this is right what largely the scientific community has agreed upon, what we can back out. And at the end of the Big Bang, this is where I'll hedge a little bit. I think you had only made up through carbon. I could be wrong. I think actually it's probably even it might have only been lithium. So I have not taught my intro to radiochemistry class in a while. And so this is where, I'll defer to some of that. But so you really didn't get that heavy, right? And it's when you started everything started condensing, you started making stars and things of that nature. And especially if you had big stars on some level, you were able to continue to burn further and further up the chain. So, in smaller stars, you might have been able to maybe get up to carbon, and then you can continue to burn up, and then maybe you're able to get up to some other elements. But really, it's once you need to get past, especially, oh gosh, now I'm going to screw this one up. Once you reach a certain point, you've got your S process and your R process as far as the rapid process and the slow process for stellar nucleosynthesis, where so the slow process is you're slowly just capturing a neutron and then it beta decays up the chain, slowly captures a neutron, beta decays up the chain. But if you really want to make something like uranium, you need to have a supernova event. So basically a star is massive enough that it's able to just explode. You get this onslaught, this massive neutron flux that's basically able to get you across the valley from, I believe it's bismuth and lead, all the way up to the rest of the elements. And so that's something that you need to be able to facilitate that.
Tons of gravity, tons of energy. Smash elements and protons and neutrons together and then get these huge molecules, elements that come out the other side, right? Yeah.
Yeah, and to kind of put it on layman's even further, it's the bigger the star, the heavier the element that you are able to make. And the fact that we have so much uranium on Earth suggests that at one point there must have been a supernova in the area that we are at. So that's always a fun
and it's like pretty
question in the
right? Like throughout the Earth there. I mean, it's been concentrated in different veins and
yeah. And then in it, so much of the concentration, right, would probably portend more to the geochemistry of how just the transfer of uranium in the environment than through some other things. But yeah.
Okay, we can back out of that rabbit hole. Thanks for indulging me. I
Sure, no problem.
Okay, so what was your PhD about, and how did you get into academia?
Right. So my PhD was basically in different forms of nuclear fuel cycle separations and nuclear waste management. And so the first part of the degree was actually focused on remediating the Hanford site up in South Central Washington State. Of course, this is something that's a legacy from our effort during the Cold War. It's in many ways, I recognize that it is a significant legacy that, is requiring billions upon billions to remediate and is very complex, but also at the same time, it's quite remarkable the level of engineering and investment that happened at the Hanford site as far as when it came to plutonium production. One of the things that complicates the remediation of the Hanford site is that there were actually 3 chemistries that were developed at massive scale for plutonium production. The first one was the bismuth phosphate process, which was actually the same process that Glenn Seaborg used when he discovered microgram amounts of plutonium. And then they basically, as far as I understand, did a scale-up factor on 10 to the 8 on this separation process, which is unheard of to any chemical engineer that you would go through and try and massively scale this precipitation process. But so that was the first one that they developed. It had its challenges, ultimately, as far as efficiency and waste and other things. And so then they moved on to a process called the redox process, which So if the first process was a precipitation-based approach where they separated the plutonium from the uranium and some other things, there was another process that they used that was solvent extraction-based. And solvent extraction, all separation processes require some form of a phase transfer, basically. Something's going from liquid to solid or from liquid to liquid, as you will talk about in an oil-water separation, but this is all some form of chemical separation. So the redox process was a solvent extraction-based or oil and water-based separation where they extracted the uranium up from an aqueous phase into an organic oil phase. I always, when I'm talking about this, as perhaps even in middle school science, you'll see people with oil and water and mixing in them together and seeing them phase separate. That's precisely what is happening here. So they did that for a little bit until they realized that it had issues with process and efficiency as well as some safety challenges. And then eventually they landed on the Purex process, which had been being developed across the entirety of the U.S. And so that really represents on many levels the state of the practice today when it comes to commercial nuclear fuel recycling. And so because of that complex chemistry that was developed at massive scale, it is a challenge to remediate it. It's not clear what is in the tanks at a given time because there are multiple chemistries happening at once. And so now if you want to clean up and purify what's in there, you don't know what's in there. And so you need to develop chemistries that can support that, and as well as approaches that can tell you what is in there. So that was kind of a first half of my PhD, and I was really focusing on the chemistry that could help facilitate that. But I, as is perhaps no surprise, I came to do my PhD work not in remediation of the Hanford site, but, more connected to commercial nuclear fuel and commercial nuclear energy. And at that time, we had the Global Nuclear Energy Partnership. This was something that was being pushed across the board as a potential pathway to enable more energy security and an approach to nuclear waste management. And so that required the development of new chemistries to help support that. And that was basically the back half of my PhD.
Awesome. That's pretty dense, but I think you did an excellent job of describing, especially like the separation process. How to get these chemistries out. Your oil and water solutions separating and separation, like there's a whole industry in the oil and gas industry that is dedicated to just that.
Right. Yeah, this is a process that scales incredibly well. It's easy to pump and move around liquids. You generally aren't dealing with massive changes in heat, or it's not energy intensive in that regard. I'm not going to say that it's perfect. I think over time people see more and more that there are environmental.
Yes, but yeah.
What's that?
So heat helps with the oil.
It does help, yeah, and it depends on what at least in nuclear fuel cycle separations, you don't necessarily need to make it heat. It might be a little bit different in the oil and gas industry.
Yeah. When people say broadly like chemistries, right, I assume that refers to like the specific molecules and then the chemical reactions that occur, like between, right? Yeah. And then I feel like the world doesn't really understand the differences between chemistry and chemical engineering, and like. Right. Oh, well, we can do the chemistry in like 2 beakers on a lab desk on a bench, right? And then when you say the scale up to 10 to the 8th, like that's a massive engineering project of like, okay, where are you actually going to put the pipes and the pumps and the tanks and everything? Right?
Absolutely. Yeah. It's just the scale of it takes me aback. And I think it's also a testament to the way that we were, of course, resourcing that effort at the time. Right. So
what do you mean by that? Like how much money the program had?
How much money we were putting into the Manhattan Project, right? So, and this was really actually after the Manhattan Project, but still.
Right. Well, there were a lot of residual effects, and Hanford is notorious throughout the industry. Was very helpful at the time. So team.
Right. Yeah. And I think that there's actually looking through that case study of the three processes, what I found was that what's interesting in that is we made choices consistently to improve the overall efficiency of the process and the purity of the process, but this was all really on some level done almost independent of really private market, right? In a way, right? The government is always beholden, of course, to its people and things of that nature, right? But they were doing this just because it was like, oh yeah, this we need to make these changes because we are seeing improvements. Oh, and by the way, actually each time we improve this process for efficiency, we're substantially decreasing the waste. And so it's kind of, in my mind, when it comes to the nuclear industry, one of our first documented examples of we can both improve the process efficiency and the quality of the process while substantially minimizing the waste byproducts associated with it. So there's already a case study that shows that.
Yeah. Okay, so without getting too far into the weeds, I guess you said
Right.
Purex process and thinking about spent nuclear fuel and recycling. Like, can you give kind of high level overview of your interest in that sector?
In that sector, yeah. So at least with respect to that, so as I alluded to earlier, the Purex process has become the gold standard for how people generally recycle and treat used nuclear fuel. This is basically the de facto process in Le Hague, which is of course where they recycle their fuel in France, as far as that's concerned. And you'll see small perturbations to that process, but it's really basically what we use today. And I think over time, what I recognized more and more is while we certainly can use the Purex process to do a lot of things, using Purex in and of itself today could potentially come along with its challenges in the fact that really Purex was designed under a couple of design principles of what it was trying to accomplish and under a couple of just general environmental circumstances. One is that we were trying to make pure plutonium, right? That was the design basis for Purex. The other one is, as I already alluded to a little bit earlier, is we really on some level didn't care how much it costed, right? This was people were not coming down to the bottom line of this and saying, "Aha!" But how much?
Name of defense and survival. Who cares how much?
Right. It was just a different scenario. And then the other piece of this is, oh, by the way, what we had known what the chemistry of plutonium was that we had known that plutonium existed for about a decade. Right? So plutonium's discovered in 1939, the Purex process comes out in 1949, right? And so we've learned, fast forward 70 plus years, we have learned a lot about the chemistry not only of plutonium, but of the other elements. And when you put all of these things together, it suggests that while Purex works, it's, people talk about things being on a TRL 10 scale. You could make the argument that Purex is on TRL 11, right? It may not actually be the right choice for nuclear fuel recycling technologies at this time because there are other factors, whether it's we perhaps need to be more economic in this because it is something that can, if you're not subsidizing your nuclear fuel recycling process like they are in France, right, it's hard to point to that and say this is something we can do. If you are being mindful about generating pure plutonium streams, well, this is something that, while at the time we needed to do because of the design basis, this is not something that we need to do today necessarily, right? We don't care if we have pure plutonium streams. What we want is fuel, right? So it just changes some of the chemistries that you might select there.
Gotcha. Okay, so after your PhD, did you have a stint between then and mines?
I did. That was during that 2-year period at PNNL, and that was where I was a staff scientist. And really it was a continuum of things. I continued to do more on the Hanford side, remediation chemistry. Of course, that's a PNNL being co-cited on some level, not quite, but with the Hanford site, that's a very nice natural part of that conversation.
Very natural partners. Yeah.
Very natural partners there, right? And then I guess the other thing that I'll say, at least with respect to my PhD research at the time, the approach that people were taking to take a fresh look at what nuclear fuel recycling would look like was some part of, and this will be very in the weeds, but they were calling it Urex. So instead of Purex, it's the Urex process where we are not generating pure plutonium streams, but it's basically you would do bulk uranium recovery, maybe with molybdenum. There were about 70 different incantations of Urex, of different ways that people could pencil out how you would get what element out at what time. But generally, you would do uranium plus maybe extraction with something else like molybdenum because of the medical radioisotope benefit. And then you might do co-recovery of neptunium plus plutonium. That way you're not generating that pure plutonium stream. And then another design basis that had evolved was Yucca Mountain, right, was now a part of our ecosystem. And there were concerns about the heat load associated with Yucca Mountain. And so people were attentive to not putting, very high, what we would call high specific activity things, but things that are basically really short-lived that generate a lot of heat, things like strontium and cesium and even americium, right? People were being mindful about should we recover them and maybe to, store them separately or do something, right? So all of those things were impacting the chemistries that people were deciding on at that time. And so that was part of how I spent my time both at WSU as well as at PNNL.
Gotcha. And then how did you make the switch over to mines?
Right. So I had thought for a while that I would eventually end up in academia. When I had about a semester off, courtesy of the nuclear chemistry summer school, I was able to graduate early. And so I had a semester between my time at CSU and WSU, and I didn't want to go straight into graduate school. And at that time, I substitute taught math and coached lacrosse, and I just enjoyed being in the classroom. And so I figured at some point I would do this. But at the time, I didn't want to because going for tenure sounded scary, right? You may not have a job after 6 years. You're hoping a funding agency loves you. And, my PhD advisor had spent about 20 years at Argonne National Lab, and then he came over as a professor, and I was like, this is the way to do it. I'll spend my time at the National Lab and not sweat the tenure process, and then they'll just accept me after a long career at the lab. And I talked with more people about this and also started to realize more and more that I love our national lab system, and I love many of my colleagues there that have done some excellent things, but it's not just you show up and they give you, here's your funding, go do things.
Yeah.
Yeah. So you're still writing proposals, right? You still have to do all of this. Oh, and by the way, there's no 6-year time horizon on your proposals. You have some projects that are longer lead time, right? But on some level, year to year, you could be actually trying, do I have funding to do what I want to do? And I was like, well, this is actually, you can make an argument in academia. 9 months of my salary are paid for. I just have to cover 3 months of my summer salary, and I have a 6-year runway. Oh, and I get a startup package. This is actually an okay deal. And so that combined with my, that makes me sound quite a bit like a mercenary, but the idea also that I already knew that I wanted to go into teaching. And so it just, that was, and then the running joke too is that, I'm from Colorado, grew up in Colorado Springs. I did not anticipate that they would be hiring an actinide radiochemist in the state anytime soon, much less at a place as wonderful in mines. I joke that you don't see an actinide radiochemistry posting in the Denver Post every day. Not that it was where I found it, but I thought that this is just a no-brainer.
Yeah. I just want to comment, I feel like people can have a biased view against academia, which is oh, you guys are just academics. You don't actually do real work, right? Industry has kind of this perspective. But when I think about the way that academia scopes projects and the effort, the amount of work that goes into grant writing and getting research funded, you guys are really good at this. Demonstrating scope and saying this is what we're going to do. This is how we're going to progress. Here's the milestones. Here's the costs. Here's the project. And it's something that I think industry could learn a little bit from, because I've had a lot of, I'll say, projects where we've spent a lot of money and they've been successful and some have been failures, but where it's literally the opposite. Like, here's a whiteboard for what we want to do. Okay, great. Go spend millions of dollars. Like,
right. And I mean, you can see, limitations in project management, both in academia and in industry, right? And, I think a running joke one of my colleagues once shared with me is, oh yeah, you go be an academic. You can work any 70 hours of the week that you want, right? You can kind of have that. But I mean, the thing is too is this can also very much be the case in industry. I've seen people work very hard in industry, and so they're both sectors would benefit from spending a little bit of time with each other, from what I've seen.
Okay, so tell me about your research group and some of the work that you guys have done at Mines.
Right. So when I started off at the research group there, we were just kind of in what you were seeing was kind of a slowdown in the GNEP approach, so the Global Nuclear Energy Partnership approach. And so a lot of the chemistries that I'd spent time developing in my time at WSU and at PNNL, you were kind of seeing the funding shrink up for that. And but I was still able to get a grant here or there, but it dawned on me that if I really wanted to have the group that I wanted, as well as, profile, tenure, kind of all of these things, I needed to be mindful of, what else I was going to do. And I think also within that space, that was my first signal that, considering when I started graduate school, I was on the big upswing of GNEP and nuclear fuel recycling, just how fickle approaches could be with respect to back-end management and approaches. And I became much more curious about why that was the case, right? And as you started, a question all this, well, why don't we recycle? Why don't we recycle? Some of that is associated with the national security matters and, thoughtfulness with respect to nonproliferation and things of that nature. And so, consistent with the drawdown in support for nuclear fuel recycling research, you were also seeing an uptick in support for things from Department of Homeland Security, for the Defense Threat Reduction Agency, and people wanting to support more of a technical nuclear forensics portfolio, which I'll kind of joke that, okay, nuclear fuel recycling, you're trying to do separations on a very large scale. For technical nuclear forensics, you're trying to do separations usually on a very small scale. So instead of doing solvent extraction, you're doing things like, not to nerd out for a second, but something like column chromatography that you can handle just, very tiny atoms amount at a time and get a very clean separation out of that. And so that was some of the time at Mines was experiencing that. I had a wonderful opportunity to serve on a National Academies panel and review, I should really say, because I was a member of it, where we reviewed our technical nuclear forensics capability of the nation, and that started to give me a broader national awareness of what that capability looked like, and a broader understanding, as well as a little bit of an insight as to how the many different ways that funding can work from the federal government and where those checks and balances sits, and just kind of that awareness there. So that was one thread that really started to get established at Mines. And certainly it's funny, but we forget that Los Alamos National Lab sometimes is just a mere 6 hours away, and it's just
feels so much further.
Right, it feels far away, but it's this incredible national resource, right? And with
just stopping
there
on the way and hit
exactly.
Yeah, really make us more motivated to go down and say hi to them.
Yeah. Right. But the other thing, so that was one thrust, and then also at the time, and this will be very niche, there was some intrigue happening at the very back end of the periodic table with respect to chemistry, things like berkelium, californium, and einsteinium, elements that nobody had probably looked at for a while. This was being initiated by now a colleague of mine. He was at Florida State at the time, Thomas Albrecht, and he was looking at this, and I actually had the opportunity to do some, what I would say, heavy element chemistry on elements that you don't find basically very many places in the world. And so between that, we were able to build a pretty diverse and robust research group. And that's basically how the group exists today.
That's awesome. I'm going to try and summarize back to you again. Like,
oh, sure.
So you started out being like, all right, why aren't we recycling spent nuclear fuel? We have these processes, the Purex process, but like you said, if you could pencil out different chemistries, different processes to extract stuff, then like maybe we could be more efficient. Maybe we could do it cheaper. Maybe we could do it faster. Maybe we could do it safer. Any of these things. I find this like fascinating about the nuclear industry in general, that so much of it is stuck in like a first iteration, like the macro process of like, all right, we found this step and it worked. And yet there's so many other ways to skin the cat that like I've seen in other industries, like trying out different things. And so that was one approach. And then saying like, all right, well, let's try out some other things for different recycling processes. And then suddenly Homeland Security said, oh, this could actually be really helpful for helping prevent proliferation stuff. And like your work got tied into that too.
Yeah. Yeah, and I would actually even say the work with non-proliferation and Homeland Security, I would even say was even more divorced from the separations efforts. So when you get into technical nuclear forensics, there's basically a couple of scenarios that you're mindful of, and I should say non-proliferation. One is the front end of the nuclear fuel cycle, so basically before anything gets into the reactor. And the idea that, so say you discover some uranium or even some plutonium in a place where it shouldn't be. Where did this material come from? Or as I've heard friends describe it, there's free range plutonium. Why did it end up here? And so there are different analytical approaches that you can use to try and back out some of that information. And especially on the academic side, what we try and do is, because we're far from application, on some level, frequently, we're trying to kind of test the robustness of the assumptions and of the chemistry that might lead somebody to be able to make a sort of assessment. So that's one thing. So there's the pre-det side on the nuclear forensics, and then there's actually the post-detonation side, which sounds as it is, right? So if you did have a bomb go off, what, based on the elemental and isotopic signatures, what could you back out from that? In order to get your hands on that information, you would actually need to do chemistry to go ahead and analyze it. And so it actually, aside from the fact that there were actinide elements, and I have a background in chemical separations, you end up in some pretty different places. And generally the idea that some chemistries transport over, some don't, but you end up heading down some different places in what you're trying to accomplish there.
Yeah. How big is the research group?
The research group right now is at 10 students. So it's vacillated anywhere between, kind of 8 and 13 in recent memory. And then I am very, very fortunate to have 3 research faculty that work with me while I've been displaced, and so they're remarkable. There's no way that I could do a lot of the things that I'm doing without basically not only the research group, but then also the management team that I have that helps support all of that.
Yeah. On the recycling side, like I guess has there been a lot of work done to advance the recycling of spent nuclear fuel since? I guess in my mind, we had this political decision that we weren't going to recycle it in the U.S. But
right,
yeah, I mean, you got into it thinking that we should, that there should be a better way to do this.
Right. And so actually, historically, if you look at what has been the timeline and sort of a series of decisions associated with nuclear fuel recycling, what you'll see is that there's, the most prominent decision that's basically been usually recognized by folks as the Jimmy Carter decision, right, to stop commercial nuclear fuel recycling. But this has actually changed hands numerous times over the course of various presidential administrations, from people deciding that we should do things to maybe backing it off to more fundamental research. And basically what you've seen has been at least a consistent emerging thread for, I'd say, the majority of the past 30 years is the government has maintained some capability with respect to nuclear fuel cycling R&D. And, sometimes we're doing more development, sometimes we're doing more research, and that's kind of what you've seen vacillate back and forth. The most interesting thing that you've seen, and this in many ways parallels what you're seeing with respect to nuclear reactor technologies, is it's not just the government investments in this, but it's also the private sector investments in this, right? So I've been pointing out to people kind of frequently recently that it's not necessary. Now, granted, I don't want to take anything away from the Advanced Research Development Project, the ARDP projects that are enabling things like X Energy and TerraPower move forward, right? But, if it wasn't for the additional private sector investment, these are things that would be really struggling, right? You have to have more than that. And I think it's actually the additional private investment. That's what you've seen right now as well, as far as other entities looking at this. Sure, the government is providing support, but it's also in partnership with whether it's companies like Shine or X Energy or Oklo or Curio or Orano, right? All of these entities are in this space because they recognize that there might actually be a value proposition on recycling when you reframe it, as opposed to just using some of the set technology that we've had historically.
What is some of the arguments for that value proposition? Like, what are the opportunities in this space?
Right.
Like, I don't see an argument that I've heard against recycling spent nuclear fuel is like, well, it's too expensive.
Right. And so that's basically, if you assume that it can be made not too expensive, for one thing, right?
Right.
If you think that,
well, chemistry, like
right, and it kind of gets into the idea of, well, when you build, depending on what type of facilities you choose and what chemistry you choose, on the back of the envelope, you can save yourself an order of magnitude, right? As far as if you're not having to build big facilities to manage additional waste streams, or you're more thoughtful in proving very efficient waste streams, or, chemistries and all these sorts of things, or how you manage your off gas, right? And so that's one piece of the equation. But the other piece of it is, and this is where I always try and hedge a little bit because it's not the strongest footing to be on, right? But as uranium prices go up, right, this also makes an impact to the overall economics. And that's part of why during GNAP, right, which was basically during the Bush administration, right, we were in the middle of what was the nuclear renaissance, and you were seeing uranium prices going up, and the value proposition on nuclear fuel recycling was going up. So that was one piece of things. But as we continue to look at this, if we are to take the tripling of nuclear by 2050 seriously, right, as far as just uranium resourcing, this is another aspect of it. I think another piece of this is, even if I also too try to be careful with that argument, because you can say, we might be resource limited, but people will quickly point out, as soon as you start looking for a resource, you're probably going to find more of it. So I feel like that's not the strongest footing to be on. But the idea that this is a much more environmentally sustainable approach, right? As far as just not having to mine as much, just stewardship of resources, things of this nature, right? There can be some benefits associated with that. And then ironically, on the non-proliferation side of the house, if you do burn your plutonium in the reactor, right, then it is not available for weapons use, right? So there are all of these things that intersect. And I will say, finally, I think that we have seen some impacts, right, with respect to being able to source materials from Russia, right, as far as isotopes and things of that nature. And that has also probably changed some of the value proposition with respect to this.
You may not know the answer to this, but do you think there's opportunity through innovation and through chemistry to reduce the end fabricated fuel cost? You mentioned the fuel cycle, and I'll add one piece of context for this. So when we look at microreactors, INL came out with a report that says that Marvel, for some nth of a kind, might have fuel cost, and I think NIA had a similar number, but like $25,000 per kilogram, which could be cost prohibitive for microreactors. But not just the raw material source, but rather through the whole fuel value supply chain. Like, is there opportunity for chemistry to play a role here?
It's been on my mind a lot, not just can you get it out of the recycling facility at an improved cost, but can you actually do the fuel fabrication at an improved cost? And my suspicion on this is I do believe it is possible, but now is that R&D happening? I'm pretty confident that it's not, right? Because one of the challenges that you do have when you're fabricating a plutonium-based fuel instead of a uranium-based fuel is that plutonium is not as easy to handle as uranium, right? So you would be miles ahead if you had more automated processes or processes that could just in general be more efficient. And every sense that I have when it comes to fuel fabrication capability is it's fairly, what's the word that I'm looking for, is it's not really terribly sophisticated as far as we have made investments with respect to our fuel fab capability that was put down decades ago. You can imagine with all the innovation in manufacturing that we have today, we might pick different approaches. So I wouldn't say it's necessarily innovations in chemistry as much as I think we've gotten so much better in robotics and other forms of manufacturing that I'd be surprised if there was an opportunity to make improvements there.
Okay, so when you think about problems, and we normally ask people like, how can people help? But I think a different way to ask this question would be like, what research topics do you find super interesting that, like, if you had a new grad student come to you or one of these advanced reactor companies or even an investor and be like, what are some of the like big problems in the space that like could be solved and might be solved in the next 1 to 5 years and that research could help with?
Right. So when it comes to solving things in the next 1 to 5 years, I do want to be a little bit careful of, because we may solve it, but we may not deploy it. Right. So those are, and so just kind of being mindful of that.
Yeah.
But I think when I've looked at
going
some
from
of
the lab to the factory is a significant amount of capital is typically required.
I think, it's pretty well documented that, from bench top to deployment is at a minimum 10 years, if not, and this is across sectors, right? But at any rate, so with respect to that, I think there are a lot of innovative approaches with respect to nuclear fuel recycling that are still underway. I think that if we made some serious investment in those, we would be able to get those de-risked to the point that you could talk about scaling. So that would be kind of my first one. We're seeing a lot of promise there, but I think that this sector does need more investment to do it the way that I've been talking about, right? And then the other place, I think fuel fab and new novel approaches to leveraging that's something that I'm very interested to see if there's something that could come about that. And then I think another piece within this, at least if we're talking exclusively back end, is when we talk about valorizing all of the different things that you can get out of your nuclear fuel, things like medical radioisotopes or, isotopes for nuclear batteries, right? It's still not clear to me, though I think people are working on it. What is necessarily the best approach for some of the chemistries that we need to select on that based on the types of fuels that people are thinking of and all of that sort of stuff. So those are things that if I had to rack and stack a priority list, those are 3 that I would come up with. And I think that we could make serious headway on those in the next, 5 years if we had appropriate investment in them.
I love that. Well, Jen or Dr. Shafer, we are unfortunately out of time today, but we've just barely scratched the surface. We have to have you back on ASAP. But yeah, this has been great. I've really enjoyed it.
Yeah, awesome, Mark. Thanks again so much for having me.
Thanks for chatting.